Dear students, today we start a very important topic. We will start with classification of the reactions. It will help you not only to classify reaction but also to predict properties of the reaction we will proceed. Today we'll also discuss hydrocarbons and their properties. Let's start with the classification of organic reactions. Uh, Something will be the same with the general chemistry, but something will be different. You will study in general chemistry exothermic and endothermic reaction, catalytic and acatalytic, and so on and so on. But for organic chemistry, the most important classification will be based on structural changes in the main substance. We will name it substrate. We will say about substitution, addition, and elimination reactions, and about some other reactions, but they will be not so important. This is the first approach, and the second approach will be based on the type of reagent. Reagents can be radical or polar, but the term polar is not very important for you. All polar or ionic reagents, they can be divided to nucleophiles and electrophiles. All these terms now we will discuss in details. The first, I used terms substrate and reagents. What does it mean? For example, we have this substance and I name it substrate, and the red substance is the reagent. Why? Because in organic chemistry usually we name the organic molecule the substrate and inorganic substance as a reagent. So now everything is clear. Yes. Uh, in the next reaction, both substances, yes, both reactant substances, they are organic. Just in this case, the situation is a little bit ambiguous. Uh, just sometime you can read such a definition of substrate that substrate is a bigger molecule given a carbon to form the new bond. Really here we see that the molecule given carbon, yes, from black molecule, and red molecule is given oxygen. Just because of this definition we can say that black cyclohexane molecule is a substrate and a red molecule, methanol, is a reagent. Just here we can see different presentations of the molecules. But in all the cases, both of them are reactants, reactant molecules. So again, definitions. Reactants in all the cases are substances that are consumed in the course of the chemical reaction. Reagents in organic chemistry, in general chemistry it will be a little bit different, but reagents are compounds, usually composed of inorganic or small organic molecules that are used to effect a transformation on an organic substrate. And usually substrate is a carbon giver to newly formed bond. Just we can see on the slide few more substances. Something green, something magenta. Just green, sometimes you will see such substances, they are solvents. And catalyst, hydrogen plus. Both of them are not consumed in the reaction. Repeating again. Reactant substances, reactants, both substrate and reagents, they are consumed in the reaction. Catalyst and solvent, they are not consumed in the reaction, but they are also important for the process. And as a result, we obtain, yes, the targeted structure, reaction product. Now again about classification, because now we know everything about substrate and reagent. The first classification is based on the structural changes in a substrate. We'll say about substitution, addition, elimination, and about few more reactions. But substitution, addition, and elimination are the main reactions in organic chemistry. Substitution reaction are characterized by replacement of an atom or group of atom, we will say about fragments, by another atom or group of atoms. Just because of the first letter of the term substitution, we will apply such abbreviation S for substitution reaction. Just aside from this group, the number of bonds does not change. Just now I will try to present you some logical scheme for substitution reaction. Let's imagine that we are replacing the ring with triangle. Yes, it's very simple. Ctrl C, Ctrl V, and instead of blue ring, we obtain triangle. This is logical scheme. But in chemistry, we usually apply the other presentation. Yes, some formula, yes, including some group to be substituted, and as a result we obtain the substitution product. Yes, again abbreviation S for this reaction. Yes, few example. Now I will scan all the course. Now you'll see the reaction from some future topics. Just I want simply to show you that this approach is universal and very important for your understanding of all the reactions. Today we will start with alkanes. Yes, alkanes, they can break only carbon-hydrogen bond. So substitution will include the replacement of the hydrogen. Yes, just very simple to predict the product of the reaction. Again, in arenes, hydrogen will be substituted. We will see in a little bit different process, but as a result we will obtain again hydrogen will be substituted with the bromine. In haloalkanes, yes, bromine can be substituted, yes, for example with OH, and we will obtain alcohol. Then carboxylic acid, OH fragment can be substituted with the methoxy group, and for example acyl halides can be substituted again with some substances. Just now I am presenting you rather difficult reaction, but again formula it's very simple. Yes, Ctrl C, Ctrl V, and now the reagent approaching our substance, and chlorine will be substituted. Just final product consists of the fragment from a substrate and a reagent from black and red. So very simple, hoping you will be able to write all this reaction by yourself. Next type of reaction is addition reaction. In addition reaction, reagents join to two atoms joined by a multiple bond. You understand that abbreviation will be A from addition. Just which multiple bond we know? Yes, carbon-carbon double bond, carbon-carbon triple bond, carbon heteroatom bond is also possible. In all the cases, reagent will join to multiple bond. Logical scheme, yes, we will destroy only multiple bond, and the rest of molecule will be the same. Yes, so just like we can see in the presentation of two frogs, yes, eating some flies, just something like addition reaction. Okay, now chemical reaction, very simple. Ctrl C, Ctrl V, we destroy pi bond and forming two new single bonds. Yes, A and B will be added. Yes, again abbreviation A from addition. Okay, some examples. For alkenes, for example, addition of bromine. Yes, Ctrl C, Ctrl V, destroying pi bond and adding to new sigma bond, bromine, bromine. Alkynes, yes, we can destroy one or two bonds. Just now you see the product of the mono addition. Then you can add one more mole of chlorine. For aldehydes and ketones, for example, we will add hydrogen, yes, we will obtain alcohol, or in abbreviated form. Yes, so very simple, and hoping you will be able to write down this reaction by yourself. And finally, elimination reaction. Elimination reaction is counterpart to addition. This is a reverse process for addition. Yes, and as a result, the double bond will be formed. Yes, formal scheme again is very simple: elimination and the formation of the double bond. Abbreviation is E. So, okay, some example. For example, for halogen alkanes, yes, we will obtain elimination to form alkenes. Yes, the mechanism include the abstraction of hydrogen and then elimination of bromine. Okay, for alcohol, it will be elimination of water, yes, and we will obtain again the alkene. Just you saw different red substances and we name them reagents. We named previously the types of reaction based on the changes in the structure of substrate: addition, substitution, elimination, A, S, E. Now we will join to these letters the new letters which characterize the type of the reagents. All reagents, I said to you previously, they can be either radical or polar. But in most cases we will see about radicals, electrophiles and nucleophiles. Please memorize these terms. Yes, and just radical or free radical is an atom, molecule or ion that has unpaired electrons. They participate in different homolysis processes, just either in the bond breaking, homolysis, or bond formation, homogenesis, the formation of the bond from two particles bearing one electrons. So here A and B are radicals. And in contrary, polar reactions tend for heterolysis, just heterolytic break of the bond, yes, to form electrophile and nucleophile, and just heterogenic formation of the bond. Yes, here we see that this particle given electron pair and hydrogen plus had no electrons on a vacant orbital at all, and just 2 plus 0 we obtain 2 electrons for the new bond. In previous example, 1 plus 1, and again 2 for newly formed bond. So radicals, they contain unpaired electrons, and nucleophile, they contain electron pair, and electrophile has free orbital. Just I think for you it will be important to differentiate different reactions, and when you will be proposed to write down some reaction, some science of radical and ionic reaction will help you. For radical reactions, the presence of some particles giving radicals easily is very typical. For example, some peroxide compounds, or some metal cations that can be oxidized easily. For example, for ferrum 2-valent, yes, we can obtain 3-valent ion. Radical reactions usually occur in the gas phase. They're very sensitive to electron acceptors, and just they are typical for substrates with non-polar or very slightly polar bonds. For ionic reactions, is very typical the polar solvents. Reactions in many cases are catalyzed by acids and bases, and in substrate polar covalent bond will be found. Just few words about arrows. You saw on previous slides the full arrow and one side or fishhook arrow. Just full head arrow show us the movement or shift of electron pair, two electrons, and fishhook arrow show the transfer of one electron. So full head arrow will be used for reactions with polar reagents, with electrophiles and nucleophiles, heterolytic reactions, and fishhook arrow will be used for radical reactions. Just now, definitions for nucleophiles and electrophiles. Nucleophile, just literally we can translate from the Latin loving nuclear, yes, is a reagent donating an electron pair to form a bond with electrophile. Nucleophiles can be negatively charged, yes, for example, halogen anions, some carbon anions, hydroxide anion, and a very important particle, hydrogen minus, hydride anion. Just maybe hydrogen plus is more typical for your understanding of chemistry, but hydrogen minus, hydride anion is very important both for synthetic organic chemistry and biochemistry. It takes part in a lot of biological processes. But some nucleophiles, they are neutral molecules, but in all the cases they contain the electron pair on nitrogen, on oxygen, or on sulfur. And some molecules containing pi bonds or aromatic systems, they are also nucleophilic. Electrophiles, they are reagents which attract an electron pair to form a bond with a nucleophile. They can be either positively charged particles, proton, hydrogen plus, chlorine plus, and some other cations, or neutral molecules, or so-called Lewis bases. We will discuss a little bit later the term. Yes, all these particles, they containing free orbital, compounds containing elements from the second and third period of the periodic table, or some compounds containing transitory metals, and some neutral molecule containing very, very polarized bond. For example, carbon, halogen, or conjugated double bond, yes. So they are also electrophiles. And a few words about acid-base reactions. This is the other approach to chemistry, to biochemical processes, and there are few theories. We will discuss only two of them. The first theory was elaborated by Bronsted and Lowry, and according to them, acid is a proton donor and base is a proton acceptor. Just let's imagine that hydrogen is connected with some atom. It can be oxygen, nitrogen, carbon, yes, and we have some base. Just base abstracts hydrogen, and acid, yes, losing hydrogen at the very same time, and as a result we obtain conjugate base, conjugate in meaning of acid. So acid and conjugate base. Acid that lost a hydrogen, and base abstracting the hydrogen uh, forms conjugate acid. Or vice versa. Yes, acid conjugate base, base conjugate acid. So, two main definitions from Bronsted-Lowry theory. Acid is a proton donor and base is a proton acceptor. And the second definition about conjugate acid and bases. Acid, after losing a hydrogen, forms conjugate base, and base abstracting hydrogen forms conjugate acid. In Lewis theory, acid is an electron pair acceptor and base is an electron pair donor. Just we can present the process of the interaction of amine and hydrogen plus in terms of Lewis theory. Amine is a base because it gives in reaction an electron pair, and hydrogen plus is an acid because it accepts electron pair to form the ammonium cation. But you can see that here definition of Lewis acids and bases is very similar to definitions of electrophile and nucleophile. Again, about Bronsted theory, all acids can be divided to OH, SH, NH, or carbon H acids based on the atom given hydrogen plus in the reaction. And bases can be either P or pi bases, yes, and again nitrogen, oxygen, or sulfur bases. It depends on which atom we will find lone electron pair. The same molecule can be regarded in two different contexts. Amine can be regarded as nucleophile in substitution reaction, and again amine can be discussed in terms of acid-base interaction. Because in both cases nitrogen is electron pair giver, but in this case it takes part in substitution reaction. It attacks electrophilic center in this substrate, and in the second reaction the base give an electron pair to hydrogen plus. So in general we can say that a base is electrophile towards hydrogen plus. Okay, this is not mistake, but usually we are saying about bases when discuss acid-base interactions. And now we will start to discuss hydrocarbons, different subclasses, alkanes, alkenes, substances containing two or few double bonds, triple bonds, cycles, and very, very specific substances, aromatic compounds. Hydrocarbons, they have very specific properties. They are hydrophobic, and because of this they easily penetrate through the skin and mucous membranes in the body. Because of this they are toxic. Now we'll discuss some chemical properties of these substances. You can see that alkanes are, or saturated hydrocarbons, they contain non-polar or very, very slightly polar bonds. Yes, carbon-hydrogen, carbon-carbon bonds. They tend to homolysis. Let's try to predict which reactions will be typical. When we had polar bonds, polar reaction will be typical. But we have non-polar bonds, yes? So polar reaction will be not typical, radical reaction will be typical. And we can only to substitute some hydrogens. So radical substitution will be very typical for alkanes. Okay, just we said that radical substitution will be typical for alkanes, but some other reactions are also possible. Elimination reaction and some isomerization reactions. And oxidation is very important in industry, but also for excretion of hydrocarbons from living cells. Few words about substitution reaction. Just we understand that only hydrogen can be substituted, so general scheme include substitution of the hydrogen with some reagent. Yes. So chemical scheme will include some radical reagent. Okay, the most widely used radical reaction for alkanes is halogenation, and we will discuss the mechanism of this reaction. Which reagents are possible? First of all, chlorine and bromine. As for iodine, it's very unreactive reagent, so it's not possible to proceed reaction with iodine. As for fluorine, it's very active, but usually it destroys the structure of a substrate. So usually it's not applied in the laboratory. So we will find some explosion. So again, the most popular reagents are chlorine and bromine. The mechanism of the reaction includes few stages, yes, and the first stage, the first step of the reaction includes the initiation, yes. Then we have some reactions, and just before the mechanism was elaborated, scientists knew some facts. First of all, they knew that light initiates the reaction. But they also knew about very interesting fact that reaction is going after lightning is stopped. And they also knew about some unusual products, for example, acetane, chloroacetane, and so on. They knew also something about reaction kinetics, and based on all these facts, they elaborated the theory of chain reactions and got a Nobel Prize in chemistry in 1957. So again, the first reaction is initiation. We need some irradiation or some free radical obtained from molecules given radicals easily, for example, from peroxides, yes? So, as a result of homolysis, we obtain two radical particles. Yes, or in other presentation. Just again, the homolysis of the halogen molecule can be initiated by ultraviolet radiation or presence of some substances, for example, peroxide or, for example, iron 2 compounds. The second step, chain propagation step, includes the interaction of the substrate with a radical molecule. You might predict the synchronical substitution of hydrogen with chlorine, but in such a case, the reaction will be stopped after we stop the lightning. But we know from the experiment that the reaction is going further, and just it has been proposed that we have no synchronical substitution. We have a multi-step reaction, and this step includes the formation of the hydrogen chlorine molecule and a new radical, alkyl radical. This is a very important step for understanding of the mechanism of the reaction. Because next step, the methyl radical, the development of the chain, will react with the new chlorine molecule to form the product of the reaction, chloroalkane, and the new radical. Crucial moment for understanding. Just we don't need lightning anymore because the new radical is formed after interaction of the methyl radical with the chlorine molecule. And we will proceed reaction, yes, again and again and again, and finally after all these steps we will obtain termination of the reaction, termination step. uh, just two radicals can be joined to each other. Yes, just because of this we have acid, unusual product, I said about it, or the formation of acid chlorination product and some dismutation reaction to form alkenes. Yes, just we have explained the formation of all unusual products. For sure, they can be found in a very small quantities, but the presence of such substances helped us to predict the mechanism of the reaction. Some other reactions. Yes, we discussed the formation of haloalkanes. Usually more substituted haloalkanes are formed. Yes, nitration, sulfuration, and also elimination reaction and isomerization reactions. But the main reaction again is the radical substitution. Halogenation is the most widely applied reaction in alkane chemistry. Just we discussed processes for laboratory, for industry, and radical halogenation is not typical for biochemical processes, but radical oxidation is very important for excretion of hydrocarbon from organism. Few words about unsaturated hydrocarbons. Abstracting 2 or 4 or 6 or more hydrogens from saturated hydrocarbons, we obtain unsaturated hydrocarbons, alkenes, alkynes, or some polyenes, and also arenes, which have very specific properties. In nature, alkenes are present in many fruits and vegetables. Some small molecules with multiple bonds, they are so-called signaling molecules. Just the larger molecules, they give plants some taste, smell, and they are widely used in dietary and in medicine. Maybe you said about carotene, about camphene, camphor. Yes, all these substances, they contain 5, 10, 15, 20 atoms of carbons. It corresponds to the multiplying fragments of isoprene. So we can name these substances isoprenoids. Yes, included carotenes, including steroids, and so on. Few words about the smaller molecules. They contain some areas with the higher electron density, and for these areas addition processes are very typical. Yes, just again we are destroying the pi bond to form two new single bonds, and we name such reaction as addition reactions. Okay, a few words about the mechanism. The first electrophile approaching to the double bond to form unstable pi complex, just without no destruction of the pi bond. And after destruction of pi bond, we obtain the new sigma bond, we obtain carbocation, and we name this intermediate as sigma complex. Pi because pi bond is present, sigma because sigma bond formed. Sigma complex corresponds to carbocation molecule, and then nucleophile adds to form the final product. Which reactions are typical for alkenes? Hydrogenation, halogenation, hydrohalogenation, hydration, but in vivo hydration and alkylation are most widely spread reactions. Few words about hydrogenation. The scheme is very simple, but we need some catalyst to precede reactions or some specific reagents, for example, hydrides. So either hydrogen in the presence of catalyst or some hydrides, for example, boron hydrides. Examples with halogens include reaction with bromine and iodine. Again, addition of bromine will give us dibromaalkane. Chlorine is also widely used for this reaction. Hydrohalogenation proceeds in the presence of pure hydrogen halogenides or their solution. For example, for hydrochlorination, both pure gaseous hydrogen chloride can be used and its solution in the water. Again, very simple, hydrogen chloride. Hydrogen bromide is also used in this reaction. Just you saw that I wrote one of two possible products, and just I predict the correct product based on Markovnikov rule. When adding a protic acid, hydrogen is attached to the atom with fewer substituents, or in other words, with the more hydrogens. So fewer substituents, yes, yes, only one substituent and left, and more hydrogens, or vice versa, only one hydrogen, yes, here two hydrogens and two substituents. In all the cases, hydrogen will be added to the terminal carbon. This is the empiric rule, but we can predict the correct product based on the stability of two possible carbocations. The addition to the terminal carbon will give us secondary cation, and addition to the middle carbon will give us primary cation. But secondary cation is more stable. Why? Because we have two donating substituents, two methyl groups, and here only one methyl groups. We know that donating substituents stabilize carbocations. The more donating substituents, the more stable carbocation. So this reaction pathway is favorable. So this product is the major product, and it will be correct, and it corresponds to Markovnikov rule. In vivo, hydration reaction is very important and very typical, and the example of such reaction is hydration of fumaric acid to give malic acid. You see here the formation from a chiral molecule, fumaric acid. Yes, it has the plane of symmetry, so it has no chiral center. This is a chiral molecule. We see the formation of a new chiral center. Because of the enzyme presence, reaction proceeds stereoselectively. We obtain only one of two possible enantiomers. Aromatic compounds contain benzene, substituted benzenes, and some fused heterocycles. Just For these substances, addition reactions are not very typical. They are possible, but in very specific conditions. But electrophilic substitution is typical, and it proceeds also via a very specific mechanism. The first pi complex is formed. It's transformed to sigma complex. This carbocation is stabilized because of the conjugation, and after elimination of the hydrogen, we obtain finally the substitution product. In the laboratory, different reactions are possible, for example, halogenation, nitration, sulfonation, alkylation, and acylation. Uh, just here you will see different products, yes? So just when you will write the nitric or sulfuric acid in the form showing the hydroxy group, you will predict easily the formation of nitro group or some other group. So all red fragments, they correspond to electrophilic particles. So hydrogen, yes, can be substituted with electrophile to give the substitution products. Bromination reaction, nitration reaction, introduction of nitro group, methylation reaction, introduction of methyl group, more general definition, alkylation, for example, acylation, benzylation, and so on. So again, here, methylation reaction, introduction of methyl group, and acylation reaction, introduction of acyl group. The fragments from acid without hydroxy group we name acyl fragments. So introduction of such fragments we name acylation reaction. Arines are very toxic for living cells. Why? Because they destroy, they can penetrate through a lipid membrane. Enzymes, they try to oxidize them to convert them in soluble in water substances to excrete them from organism. But just in many cases we obtain again toxic, mutagenic and carcinogenic intermediates because of formation of epoxides and some other substances. In general, I said to you that excretion of hydrocarbons includes oxidation or acylation because as a result we obtain soluble in water compounds that can be excreted from the organism. But for benzene, only one variant is possible. It will be oxidation and we will form some very toxic epoxides. But for methyl group, one more enzymatic process is possible, the oxidation to carboxylic group, and benzoic acid is a non-toxic compound and it can be excreted easily from the organism. That is why toluene is less toxic compared to benzene. Again, why? Because it contains methyl group. Methyl group can be oxidized to carboxylic group, and benzoic acid, benzoate anion, non-toxic and soluble in water. It can be excreted from the organism. Oxidation of benzene give us toxic epoxides, so toxicity of benzene in general much higher. But some biologically important molecules, they contain benzene ring. Why they are not toxic? Because their oxidation, their excretion from organism, they are controlled by a specific enzymatic biochemical pathway, given no toxic products. Next time we will discuss monofunctional hydrocarbon derivatives. I will remind you a few facts about types of reactions. Hoping now you are able to write all the reactions with hydrocarbons.